When we learn about quantum mechanics, we are usually taught to picture a definite particle. The assumption is that before we ever look at it, this particle possesses independent, concrete properties like position and momentum. Werner Heisenberg established that measuring one of these properties inherently disturbs the other. If you pinpoint a particle's exact location, you lose track of where it is going. This animated diagram illustrates that mathematical limit. As the accuracy of position increases, the accuracy of momentum decreases, and the combined precision is bounded by a strict boundary known as Planck's constant, or h bar over 2. Conventional physics treats this uncertainty as a limitation of our tools. It suggests that a true, exact reality exists, but human measurement is simply too clumsy to access it. Historically, experiments were designed to uncover pre-existing facts about the universe. The lab was a place to observe a nature that existed identically whether you were looking at it or not. This creates a hidden assumption in the standard textbook reading. We assume the particle actually has a true value, hiding right behind the curtain of our measurement limitations. Because of this assumption, scientists are forced to view the act of observation as an artificial interference rather than a natural mechanism of the universe itself. For decades, physicists have conducted hidden variable experiments. These are attempts to find those secret, intact properties that we assume must exist outside of our view. They consistently fail. These experiments fail because there is no independent value hiding behind the curtain. The variables were never there to begin with. The observer-dependent theory of everything, or ODTOE, approaches this entirely differently. In this framework, quantum uncertainty is a structural property of a system that hasn't been resolved yet, rather than a lack of human knowledge. This diagram maps the ODTOE equation. A raw state, psi, enters an observer lens, operator O. The output is R, a defined reality. This operator forces a property to resolve first. This is constitutive indeterminacy. Position and momentum do not exist until forced into configuration. In ODTOE, uncertainty represents the pre-resolved state of the universe, existing as potential before it is co-constituted into a configuration. Think of reality as a raw physical resource. To take that fluid potential and solidify it into a definitive, structured form requires work. Through this mechanical lens, we can redefine Planck's constant. This box represents a fixed energetic budget. In ODTOE, Planck's constant is the minimum coherence cost, the quantum of work required to pull a configuration into reality. You cannot simultaneously resolve infinite position and momentum. The configuration lacks the internal coherence to afford both. The Heisenberg limit is a literal, physical budget required to build a shared reality. If reality requires an observer to expend energy to resolve it, we must analyze what happens when multiple observers look at the exact same system. Theories like cubism stop at treating quantum states as subjective human beliefs. ODTOE provides a rigorous structural architecture, the configuration field, to explain exactly how multiple observations interact. ODTOE posits that an observer's internal focus and emotional state dictate how efficiently they apply the operator. When internal contradictions are low, a higher fraction of the coherence budget is directed toward the measurement, allowing for sharper resolution of variables within the same physical limit. When two observers share a configuration, their joint uncertainty doesn't simply add up. It weaves together through a precise, coherence-weighted mathematical formula. The observer's internal state physically determines the resolution of the universe, directly connecting human focus to the mechanics of the quantum world. For the working physicist, the operational mathematics remain unchanged. You still calculate the exact same matrix elements and solve the same Schrödinger equation. Only the interpretation changes. Those calculations describe a co-constituted configuration of the observer, the apparatus, and the state combined, rather than a solitary isolated particle. This diagram illustrates how the wave-particle duality dissolves under this framework. Waves and particles are just different geometric configurations, forced into resolution by different types of observation. The measurement problem dissolves once we treat observation as the mechanical process that generates reality's properties, rather than a disturbance of them. We are not passive spectators staring at a hidden universe. With every observation, we are actively and continuously co-constituting the fabric of reality.